Welcome to Unit 8. Unit 8 is all about estimating area under a curve. This is definitely different than what we've been doing before, but it's kind of similar in that we are going to relearn a geometric way, and then we're going to do the same thing using calculus in Unit 9. So right now we're going to stay in just geometry using either area or area of a rectangle or area of a trapezoid. This unit might be a bit confusing in that we're not learning a lot of calculus, but I've really tried to pare it down to exactly only the things that you need in order to be successful on the exam and not the extraneous information. Although the extraneous information is really good for understanding, we don't really have a lot of time this year to learn material that's not necessarily going to be assessed. Unit 5.1 is all about estimating area under a curve. So that's what we're going to be spending the rest of our year on, estimating the area under a curve. As the first part of the year, we spent the entire time on finding the slope of a tangent line, that being the derivative. We're going to now spend the rest of our time on estimating area under a curve and eventually finding the exact area under a curve. So in 5.1, the first way they explain we could do it is by drawing little rectangles underneath the curves and then adding those rectangles together. So the important parts to note here is that there's a little bit that's not quite right. We're missing this piece, and we're overcounting this piece, and this piece, and this piece. So that's why these are just estimates. They're approximate areas under the curve. So on example 1 on page 383, we're being asked to find the approximate area A of a region enclosed by the graph f of x equals 1/2 x plus 3, the x-axis, and the lines x equals 2 and x equals 4. So here's a picture of what's going on. We have our equation of our straight line that they've given us here, and then we have another line x equals 2 and another line x equals 4, and then this line for the x-axis. And what they're asking us to figure out is what is this area right here. Now, some of you may notice that it's a trapezoid, and if you did see that it's a trapezoid, good for you. We're going to be getting to that in a few minutes. But for right now, we're going to talk about drawing rectangles under the curve. So you can see there's two different ways we can draw a rectangle. We can draw a rectangle that either underestimates it, so this would be a rectangle of a length of, 4 and a width of 2. So my area would be 8. Or we could draw a rectangle that overestimates it, which would have a length of 5 and a width of 2. So my area would be 10. And all I know is that my real answer is somewhere in the middle. It has to be in between 8 and 10. And that's really all that I know as far as what my area is going to be. So one way to make a better estimate would be to divide this picture in half and draw two smaller rectangles. So hopefully you see that this area that we're underestimating is going to be less. So let's take these two rectangles. This is a width of 1, and this is a height of 4, and this is a width of 1, and this is a height of 4.5. So my area is going to be 1 times 4 plus 1 times 4.5. So I got the 4.5 by plugging in 3, because this point is 3, into my equation. So 1/2 of 3 plus 3 is 1.5 plus 3, and that's where my 4.5 came from. So let's see, my new area is going to be 4 plus 4.5, or 8.5. And then the other way I could draw my rectangles, let me just erase what I have here, is to overestimate. So I'm still going down to 3, but here I have a little piece above my curve. So let's see, this area is going to be a 1 by 5 and a 1 by 4.5. So the area in my blue is going to be 1 by 5 plus 1 by 4.5, or 5 plus 4.5, 9.5. And now I have an area of 8.5 is less than my area is less than my 9.5, my overestimate and my underestimate. My real area is somewhere in the middle. That should be an area. Now that's a tighter range than the one we did on the previous slide, which was between 8 and 10. And someone might be able to say, well, what if we cut it into even smaller rectangles? Let's do that for a second. If I cut it into even smaller rectangles instead of going to 3, what if I went to like 2.5? And hopefully you'll see that these areas are even smaller. So we could get a more exact answer by increasing the number of rectangles. So this slide is a whole bunch of definitions. So let's just talk about it, and then we'll go through each one what they're talking about. For our purposes, we will refer to the area enclosed by a function y equals f of x. It's going to be greater than 0. On the previous slide that we talked about, we're only looking at positive area. The x-axis is going to be one of the bounds, and then x equals two different numbers, a and b. So that's our start and our end point. And we're going to refer to that as the area under the graph from a to b. So in our previous one, it was between 2 and 4. We divide or partition the interval a to b into non-overlapping subintervals. So the first interval we did went all the way from 2 to 4, and the next intervals was from 2 to 3, 3 to 4, and then the final interval that we talked about was from 2 to 2.5, 2.5 to 3, 3 to 3.5, 3.5 to 4. Those are our partitions. The length of these intervals is delta x, which is the difference between the start and the end, divided by how many intervals we're going to use. The height of the intervals is f of each partition, and that's how I found the 4.5. I plugged my x values in. And the area of the rectangles is the base times the height. And then the total area is the sum of all of them. And this summation symbol I'm sure you have not seen before, so let's just talk about it quickly. This says the sum from I goes from 1 to n of the function f of c of I times delta x. So the summation, just the symbol, means summation, and it's the sum from 1 to n is how I'm going to say that. So as we saw in our previous example, we can lead to either an overestimation or an underestimation. An overestimate is called an upper sum, and an underestimate is called a lower sum. So now here's the formal definition of everything we've spoken about. Area A under a graph of a function from a to b. Suppose a function f is non-negative and continuous on a closed interval a to b. You partition a to b into n subintervals of length delta x. The area A under the graph from a to b is the number a, which is the limit as n goes to infinity of the sums, which is the limit as n goes to infinity of the summation from 1 to n of each one of the areas of the separate rectangles.